All right, guys, I think we're going to get started. We have some very exciting information to share with you today. So first, I want to say thank you for joining us this morning, this afternoon, or this evening, wherever you're coming in from. Welcome to the What's Next webcast Beyond BOPP, unlocking higher temperatures with low loss in nanolayered polymer capacitor films. So if you haven't heard, now is the time to start looking at BOPP replacements in our capacitors today. Sorry, Mason, that was allowed, just so you know. We heard you. Um, okay, so obviously heat waves, natural disasters, the increase in power demand, the aging infrastructure, everything is compounding on our infrastructure and our ability to deliver and provide the right amount of energy at the right time and the right place. And today we're going to hear from Dr. Mason Wolak. And
Morning, everyone.
good morning. Thank you for joining, Mason. Again, I'm going to be your moderator. I'm joined by Casey Hewitt. She too is going to help us along with answering any questions that we may have during this session. And just a couple of housekeeping items. First, we are recording this session and we will make this recording available along with the slides and any other pertinent information that is valuable for you. At the end of this session, within 24 hours, you will get the recording and the deck itself. In addition to that, we ask that you also participate and submit any questions you might have through the Q&A. At the end of this session, we will open it up to a live chat, and Dr. Mason and company will answer any questions you might have at the end of the session. And in addition to that, we have a series of What's Next webcasts. And so if you're interested, please take a look at peaknano.com for all of our other on-demand sessions. And without further ado, please stay engaged and ask plenty of questions throughout this, and we'll get to them at the end of the session. Dr. Mason, or Wallach, I'm going to turn it over to you.
Okay. Thank you for the introduction, Cindy. So to give some context for the presentation today, I'll be talking a little bit about the different capacitor films that Peak Nano makes and why high performance value-added capacitor films are necessary in today's power electronics world. And to give some context here, I think we'll start with looking at the demand for electricity moving forward. So our partner Ignition Research is projecting that there should be somewhere on the order of 100% increase in electricity demand over the next 25 years globally. And this is driven largely by data centers, the exploding need for data centers, and also by EV charging and such, in addition to just general population growth. So the driving markets here, if I can. Sorry, we did a dry run earlier and advancing the slides was perfectly fine during the dry run, but of course is not working when we're live. Cindy, can you take over control? Can you move forward the slide, please? My apologies, everyone. So driving this need for expanding electricity is, of course, the explosion in electrification initiatives such as EVs. So you'll need EV charging, modernization, and expansion of power grid, both domestically in the US and across the world. And then, of course, emerging technologies such as fusion energy, need for data centers, and also defense. So all of these application spaces are really driving the need for better energy storage solutions. And at the core for energy storage solutions is typically capacitor films. Cindy, next slide, please. So capacitors are used in electric grid for power factor correction and high voltage DC. They're used in power electronics. We already talked about EVs and EV charging, renewable energies, industrial automation, a variety of different applications there. And then in pulse power, there's uses in military and defense. And additionally, one of the areas that we anticipate exploding demand for capacitors is in fusion energy. So in order to generate the fusion energy, you need a pulse power system to ignite the plasma and also to maintain the fusion reactions. So shown here on the right are a variety of different plastic film capacitors in different formats, and these can range from very, very small devices that would be surface mounted on PCBs up to large capacitors that can contain hundreds of pounds of capacitor film. Next slide. So the current de facto material that's used globally is biaxially oriented polypropylene. So you'll hear me use the term BOPP to refer to biaxially oriented polypropylene. I'll also refer to it just as polypropylene on its own. This is a great material. It has 50 years of manufacturing behind it, so people know how to make it in very, very high purity with very high yields. The material itself can withstand very high electric fields, so it has high breakdown strength and it also has very low electrical loss. Furthermore, it's very inexpensive, so consequently, it's an excellent material to use for many of the existing applications in areas like grid and EV charging. But as we move forward, these applications are becoming much more demanding. We're requiring higher temperatures and requiring higher switching rates. And so this legacy material is basically going to be in a place where it's no longer usable in these more demanding applications. Next slide, please. So the limitations here really are that the fact that there's no US manufacturing of polypropylene. So 80% of the film that is used in the United States is sourced from adversarial supply chains, and 100% of it comes from outside of the US. The material itself has a very low dielectric constant. So the dielectric constant is essentially a measure of how much starch or charge you can store per unit volume in your capacitor. So it would be desirable to have higher dielectric constant materials that can store more charge in the exact same footprint. And additionally, BOPP has pretty poor thermal characteristics. Typically, films are rated only up to about 105 degrees Celsius, and you will see voltage deratings to get into those higher temperatures. So these thermal limitations are a considerable challenge as power electronics, for example, is moving towards using high frequency silicon carbide switching. And so these environments are typically in the range of 125 to 135 degrees C. So if you want to use polypropylene in this sort of environment, you have to do elaborate cooling of the capacitors to keep them from melting. So our job at Peak really is to design that next generation of high performance film that can be used in these really demanding high temperature and high voltage environments. Next slide. So looking at BOPP and how it performs as a function of temperature, this is an example of a lifetime curves taken from a data sheet for DC link BOPP capacitors. And I'm not going to go into this in any great amount of detail, but each one of these curves are basically based upon the operational temperature that you're using the device. And what you see is if you're using the BOPP at 70 degrees Celsius, for example, you can expect very long lifetimes. But if you go to much higher temperatures, your lifetime goes down by orders of magnitude. So for example, if you go to 125 degrees C, so this is the curve in the far left bottom corner, you can expect only about 200 hours of lifetime at 125 degrees C, and you have to derate the capacitor by 50%. So if the capacitor itself is rated for 1,000 volts, for example, you'd have to use it at 500 volts maximum at 125 C, and you can expect only 200 hours of life under those conditions. Whereas the capacitor itself at room temperature might survive up to 100,000 hours at twice that voltage. So really what we're looking for is a material that can withstand that high temperature and high voltage at the same time and compete against BOPP and better BOPP really. So this is where Peak Nano comes in. Next slide, please. So we have a proprietary technology where we nanolayer our film, our capacitor film. So typically what we will do is we will take two different polymers. Both of these polymers will have different electrical, thermal, and mechanical properties, and we will stack them on top of each other inside of the polymer film. So the interior structure of the film will have many tens to hundreds to even thousands of layers depending upon the application that we're designing for. So on the right-hand side here, you can see an internal structure of a film. This is a 128 layer film with alternating layers of two polymers that have different thermal, dielectric, and mechanical properties. And depending upon which materials we put into our nanolayered films, we can completely and totally tune and change the property sets. So we have at present, we have two different families of film. One is the NanoPlex HDC film. This is a high dielectric constant film, and this is designed specifically to deliver very, very large charge storage in very small devices. And then we are developing another family of film called NanoPlex LDF, and this is designed to mimic the electrical properties of BOPP, but do so at higher operational temperatures. And most of the focus today will be on the LDF film, but I'll touch on HDC a little bit as we go forward here. Next slide, please. So to give you a little bit more detail, the HDC film, you have two different materials. One is a high dielectric constant material. One is a high breakdown strength material. So in the middle here, you have a hypothetical layer structure where resin A and resin B are stacked on top of each other. So what we can do is change the relative amount of the two materials. For example, we can make the A layers really thick and the B layers really thin, and then you would have a very high dielectric constant of anywhere between 4.5 to 6.5. But if we change that ratio and make the A layers really thin and the B layers really thick, then we can go to a lower dielectric constant material that might have a little bit higher or a little bit lower dissipation factor. So we can really design the internal structure of the film specific to different applications. So this material was originally invented and designed for pulse power applications. It excels in film foil format capacitors, where you're really delivering, let's say you have large banks where you're delivering megajoules of energy for low duty rate pulse power applications. So next slide. The new family of film that we're developing is the LDF film. And this is designed more for things like power electronics, high frequency switching, anything that is going to be using a silicon carbide inverter, for example. And what we're really trying to do, or not trying to do, but what we're achieving here is mimicking the dielectric properties of polypropylene, which is that very low loss and high breakdown strength, but moving the operational temperature to much, much higher temperature. So instead of being capped at 105 C for operation, moving into 125, 135 degrees C. And this film can be made in very thin formats down to about 3 microns, and also thick film in anywhere in between. Next slide, please. So touching on the HDC family of film, this is the high dielectric constant film, as I mentioned before. We have two commercial offerings right now. So you can contact me at any time and I can set up a discovery meeting and we can talk about what your company's needs are for capacitor films. And then I can recommend which material would more closely be suited for your needs, for example. So out of our two commercial offerings, one is a lower dielectric constant solution, which has dielectric constant of 3.7, which is actually quite high compared to other commercial films. And our 4125 family of films actually has dielectric constant just under 5. So this is really optimized for high energy storage. It does have a little bit higher dissipation factor, but that which limits it to more like pulse power type of applications. Next slide, please. So for our HDC film, we're in the process of qualification with multiple cap manufacturers. One of the envisioned applications would be something like a mobile grid solution where you could put a bunch of capacitors, more or less a substation on the back of a tractor trailer, and the caps could be set up to store much more energy. We're typically seeing between 2 and 2.5x higher energy density over BOPP in the capacitors that we've been prototyping. What you can envision here is you can put 2 to 2.5 times as much energy on the back of a tractor trailer in your mobile solution here. Other applications, of course, are pulse power, so something like firing a bunch of lasers to initiate a fusion reaction, or sparking a plasma for fusion. Next slide. Switching over to our LDF film, this is a developmental film. We are in the process of scaling our production and scaling up our plant to enable production in the millions of pounds of film. We anticipate that production quantities will be available in Q1 of 2027. The LDF film is really stacks up directly against BOPP. The dielectric constant of the film is slightly higher than BOPP, but the dissipation factor is on the exact same order of magnitude. It's around 0.03%, so it's the tan delta is more or less in the 10 to the minus 4 region. But the nice thing here is you can drive this up to 150 degrees C and maintain the dissipation factor at the same level, whereas if you go up to 150 degrees C with polypropylene, the dissipation factor shoots way up, which can lead to thermal runaway in devices. The other thing that we see here for our film is that our breakdown strength at elevated temperatures is actually higher than BOPP, and this allows us to design capacitors that don't need the same level of derating that you would get with a polypropylene-based capacitor. Next slide. So at the film level, and this slide shows 3 different properties that are pertinent for capacitor design. We are benchmarking against industry standard BOPP films. So all of the data here that's in red is our industry standard film, and everything that is in blue is our LDF film that we're in the process of developing. What you can see here on the left-hand side is the dielectric constant is much more stable out to higher temperatures than BOPP film. So for example, the point at which 2% of the initial room temperature capacitance is lost is around 105 degrees C for BOPP, but for LDF film, it is around 145 degrees C. So you have much better stability out to higher temperatures. The breakdown strength of the film at high temperature is considerably better than BOPP. So again, here you see typically a fall off of breakdown strength by about 25% lower for BOPP once you get up into 135 degrees C realm, whereas the LDF film maintains more than 90% of its room temperature breakdown strength at the same temperature. The other thing that is very attractive about the LDF film is the shrinkage of the film is much, much less than the shrinkage of BOPP. So once you're over about 125 degrees C for BOPP, the film starts to shrink in the transverse direction considerably. This is a very serious problem if you're making a metallized film capacitor, because you start to pull away from the end spray and that degrades the performance of your capacitor. But you can see on the data here on the far right that the LDF film maintains shrinkage of below 0.5% up to 150 degrees C. So what this does is it allows you to wind capacitors and cure them at higher temperatures. And typically that curing temperature is really going to set your upper thermal limit for operation of the device. Next slide, please. All right, so how do we do this? What we do is we take commercial capacitor grade polypropylene and we layer it against a high thermal stability material. So we make very thin layers of this high thermal stability polymer and then stack larger, thicker layers of polypropylene in between that more or less scaffold of the thermal stabilizing material. It's necessary to optimize the layer structure here, and this is done through judicious choice of the high TG material that we put into the layer structure, and then controlling the volumetric composition, number of layers, and thickness of layers. Next slide, please. We are in the process of prototyping with multiple cap manufacturers, so we've made a number of different rounds of prototypes. and different formats and different sizes. So we've ranged from 2.2 to 50 microfarad. This appears to be the micro is not uh, it's not millifarad devices. These are microfarad devices. The 50 microfarad devices are typically around 2 to 2.5 inches in diameter. So these are some of the different formats that we've made. And we've done cylindrical windings as well as some flat pack windings. Flat pack windings, of course, are designed to maximize energy density, so you can put multiple windings inside of a larger device to get high temperature and high current handle, or to get high voltage and high current handling. Next slide, please. In the devices that we're making so far, we're seeing dissipation factor on order of BOPP. So as you can see here, in two different prototypes, our dissipation factor is on the order of 2 times 10 to the -4. This is the same region that polypropylene sits in. So the nice thing about this low dissipation factor is that the films don't self-heat when they're subjected to high voltage. Next slide, please. And then what we're seeing again, the properties that I described earlier, where the dielectric constant stays high as a function of temperature, that holds through in the devices that we're making. So we're seeing the same sort of stability in the capacitance of the device up to about 145 degrees C. Whereas for the BOPP devices that we've characterized, these are commercial off-the-shelf devices, we're seeing the drop in capacitance happen at much lower temperatures. Additionally, you see the dissipation factor is stable out to about 150 degrees C. We have some new internal testing data. We've taken some devices up to about 150, 160 degrees C and compared them with polypropylene devices. Polypropylene devices typically see an increase in dissipation factor once you're out over 125 C, whereas our LDF film does not. Next slide. So circling back to the film properties, where shrinkage is really important, this is a good visual representation of how this property at the film level translates into making a device. So on the right-hand side here, you see 4 separate windings that were cured at different temperatures ranging from 125 to 155 degrees C. So the farthest right capacitor here, or winding here, was cured at 155, and you can see that there's some shrinkage in that device. But when we've cured from 125 to 145, we typically see very, very little change in the dimensions of the device. And then when we put end spray, we've actually cured devices that have end sprays on them, and we see no change in dissipation factor or capacitance as a function of this cure temperature. So as I mentioned before, what we typically find is most capacitors are cured at a temperature above the operational rating. So the ability to cure up to 145 degrees C here is a game changer versus polypropylene. Next slide, please. Again, this dimensional stability is super important. So we've taken some LDF-based capacitors and some BOPP-based capacitors, put them in the oven up to high temperatures. What we see is we can take an LDF-based cap, run it up to 170 degrees C, and there's no physical changes or deformation to the capacitor, whereas BOPP-based capacitors start to fall apart once you're over about 150 C. So on the right-hand side, you can see where the end spray is pulled away from the film. This is a capacitor that was run up to about 160 degrees C. If you look at the capacitance of this device and the dissipation factor of this device, the capacitance has gone way down, the dissipation factor has gone way up. So whereas the LDF device that was heated up to 170 maintains the same capacitance and the same dissipation factor. So again, this is another illustration of how the dimensional stability that's afforded inside of the film based on this high TG polymer scaffold pays off in actual device performance. Next slide, please. All right, so when we think back to the illustration of lifetime versus temperature and electric field that I showed earlier in the presentation, the ability to withstand high voltage at high temperature is really key to getting that long operational lifetime and to avoid derating the devices, right? So this data set shows that our NanoPlex film maintains high breakdown at very high temperatures. So what we're seeing here, or what we're showing here rather, is a change in breakdown strength from room temperature to high temperature as a function of temperature. So once we're over 85 degrees C, our devices maintain high breakdown strength, whereas BOPP devices start to fall off at that 85 degrees C area. So in the included graphic here, we're showing two different formulations of LDF in green and orange data. So these capacitors maintain 92 and 98% of their original room temperature breakdown strength up at 135 degrees C. So the light blue and the dark blue data is commercial off-the-shelf BOPP-based capacitors that lose about 35% of their breakdown strength when you're up around 100, when you're up at 135 degrees C. But you're also already seeing degradation and breakdown strength at 85 C as well. So our films are performing better at 135 than standard commercial BOPP films perform at 85 degrees C. So the next step here really, of course, is to do to prove out lifetime. So high temperature, high voltage over long periods of time. So we're in the process of life testing with our films right now. Next slide. So the last bit of the puzzle, of course, is that you want to have excellent self-healing of the film. So self-healing is essentially in your wound capacitor device that's under high temperature and high voltage. You will still have defect points inside of that capacitor that will have small scale failures. The desired characteristic here is to remove the electrode at the point of the failure so that the failure is electrically isolated from the rest of the capacitor. NanoPlex LDF film does this remarkably well, and you can see in this image here that when we tested the film at very high temperature and high electric fields, we have some internal failure points, and this is disassembly of a capacitor that was fully functional. We do have some internal failure points, but we're able to clear off the electrode at the points of those failures, so the capacitor itself still maintains functionality. Next slide, please. All right, so that's everything that I have for today. I'd like to basically point out that Peak Nano is moving towards, let's say, value-added solutions in the capacitor film field. Our HDC formulation provides very high energy density, so you can decrease the size and footprint of devices that are used in pulse power applications, for example, whereas the LDF formulation provides that very low dissipation, low loss performance, and high breakdown strength at very high temperatures. And if you are interested, if your company is interested in sampling Nanoplex film in either one of these families, please feel free to contact me and learn more. And at this point, I'm going to turn everything over to Cindy.
All right, Mason, you and the team have been extremely busy,
Yes, we
obviously.
have.
Wow. We have several questions from our audience, so I'm going to get started here. Our first one comes in. The question is, what is the experience in field practical data of power capacitors using HTC films?
So the vast majority of the HDC film capacitor prototyping that has been done is geared towards pulse power applications. Um, the film itself was actually designed and it was invented and designed under some funding from the Office of Naval Research, specific to some electromagnetic weaponry. Um, and the design of that particular system was a low rep rate, fire a couple times a minute type of thing. So we have manufacturers that are making capacitors with this film that is designed for lower rep rate pulse power. Typically, depending upon which family or not family, but which flavor of film, the energy density is about 1.6x to about 2.5x over polypropylene. This enables much smaller devices to be made, so you can condense down the size of the pulse power system. And then there's additional gains besides the energy density of the individual caps. You also have shorter interconnects, so you have less impedance that you're fighting against in the system. So you have much more efficient systems. We're also looking at this for mobile grid applications. And for example, we've looked at being able to deliver much higher capacitance in smaller volume devices. Breakdown strength is typically at or above polypropylene. So again, this is a little bit different type of application. If you're going to put this in a mobile application, so a substation on the back of a tractor trailer, for example, this is not a long-term solution. This is more of a hey, our substation is failing. We need to hook up to get it back up online. Um, so LDF is definitely the solution that's better for power electronics, higher rep rate type of applications. HDC is much better solution if you're looking to pack as much energy density into as small devices as possible.
Well
Hopefully
said.
that answered the question.
Yes. An extension to that question is you mentioned extended life expectancy. Do you have an idea about what that lifetime expectancy is at this time or at this stage?
So what I can say for HDC, we have done made capacitors that have been put up on shop machines that basically simulate the type of duty cycle that the capacitors are designed for. We have feedback from multiple manufacturers that we can get into the hundreds of thousands of shot cycles. Um, that's what we've been able to accomplish so far. We have ongoing tests to see exactly how far past the 100,000 shot life we can get. When it comes to LDF, because this is a developmental film, we are working with multiple manufacturers right now that are doing life testing. So initial life testing is looking at 125C or 135C at a variety of different electric fields, so we can kind of build out those lifetime curves to determine what the voltage rating would look like at different temperatures. So we're targeting 135C operation at 150 volts per micron or higher. Some of the testing is going up to 200 volts per micron. And it's just a matter of time. It's a lot of wait and see when it comes to lifetime testing. If you're designing a test for 2,000 hours, there's no way to go faster unless you have a time machine. And 2,000 hours is 2,000 hours, so it's almost an entire quarter of a year. So as that data builds in, we will be releasing that to customers.
Thank you, Mason. We'll continue to watch for that information as it evolves. And a little more clarity behind that question I have, and I apologize if I butcher this, but it says, I mean AC 60 hertz slash 50 hertz power capacitors. Would that also combined with fluid?
Yeah, so our HDC film, we've done some extensive internal testing on fluid compatibility, and some of our partners that are looking at this material have also done the same testing with fluids. Um, we've seen good compatibility. It depends on what the chemistry looks like, but we have internal testing that we could feedback. So if someone who's interested in grid space were to contact me, we can walk through which materials work well, which fluids work well with our film, and which ones are more problematic. The nice thing here is that um, because of the way that we make the film, we can actually control the exterior chemistry, so we can actually reverse the structures. You can have resin A on the outside, or you can have resin B on the outside. So it turns out that depending upon the fluid that you use, there's different structures that we can build into the film to make the film compatible with the fluid. We have found that multiple different manufacturers use different types of fluid, so it's obviously something that's very important for us to understand, and we can define that in discovery meetings with manufacturers, and we're always open to conversations, um, looking for um, partners for development and of course sales as we move forward.
Thank you. Another more of a comment, an observation for specific application, high temperatures could be a constraint for AC power capacitors, but at the normal range below 60 Celsius, both BOPP, LDF, HDC performs about the same. of course, you've demonstrated today that there's the high energy density is desirable and justify the application.
Yeah, I think, there's BOPP is not going to go away. There's going to be places where BOPP is, it's the suitable answer, right? Um, and we're not necessarily looking to replace the entire BOPP market with LDF. What we're really looking at is strategically what applications make sense. Where do you actually need that added performance? So if you're making a AC power cap for a substation, maybe you don't need LDF. Maybe BOPP is perfectly suited for for your application. We do know that if you're working with a silicon carbide inverter module and your capacitor is right next to it, you probably do want it to survive at 125 degrees C. So it's really about having the conversations with the end users and having the conversations with the cap manufacturers, understanding what their requirements are, and then kind of going through our portfolio and saying, well, we think this film right here in this formulation is the right solution for you. And that's what our team is really good at.
Good answer, right? It's positioning. It doesn't go away, but we definitely complement and enhance. All right, next question is, what different LDF film thicknesses do you anticipate offering when you go into production?
So we anticipate we've been making film between 3 and 10.5 microns so far. We anticipate having a range from 2.5 to 12 when we have production. Um, Once we have our own lines up and running, that will give us some more versatility on where we can go in terms of thickness. Um, Over time, as we scale, of course, we would have dedicated lines that would be, dedicated for thicker films and thinner films. And that's kind of part of our longer term plan is identifying which markets require which thicknesses of film, and then building that scale up plan based on the demands that we see in the marketplace.
Nice. Next question is, you've talked a lot about capacitors and replacing BOP. Will LDF or HDC change the form of our existing capacitors today?
I don't think so. I think most of the manufacturers that we've been speaking with, at least early stage prototyping, is typically wound capacitors, dry metallized film. We're expanding for LDF into film foil formats. With HDC, we actually find that HDC performs best in those film foil formats. With LDF, it's geared very much towards the metallized film. But uh, with the manufacturers that we're currently working with, um, we are we're really working with existing designs. So most of the manufacturers, the first thing they do is they pull up their winding recipes for BOPP, and then they'll put our rolls up and see whether or not they can replicate their existing recipe. And the film that we're making right now handles very well, and in most cases is a drop-in replacement. So there's not a lot of engineering that the cap manufacturers have to do in order to change up how they're actually making the film. So if you have, for example, for LDF, if you have an existing design, you have an existing tensioning that you put in, existing burn off of the start and the end of the film. Our LDF film performs very similar to BOPP, so you can actually use those existing recipes, just drop our film in, and then use that as a starting point. And maybe you have to tweak a little bit, but it's we have several manufacturers that are more or less just using the recipes that they already have in place to replicate the capacitors that they currently have as product offerings, and then look at that high temperature performance.
Nice. So less disruptive, I guess, of an
Yeah.
upgrade. Uh,
That's not to say that we're not interested in pushing the envelope on new formats for capacitors. If your company is interested in new manufacturing, we're all there. We love to push the envelope. We love to do experimental work. So please contact me, and we can have those conversations.
Mason, where are Peak's manufacturing facilities?
We're in Cleveland, Ohio, or outside of Cleveland, Ohio.
Okay, nice. Another question. Has your testing been around aluminum metallized to LDF film or zinc metallized to LDF or some other metallization?
So far, we've been focusing on aluminum. One of the things that we're certainly interested moving forward is to expand our knowledge of metallization with respect to the film. Um, so one thing that I will say is the surface chemistry of the LDF film is more or less the same as the surface chemistry of polypropylene film because we have polypropylene as our outer layers in this film. So if you can metallize it on polypropylene, you can probably metallize it the same way with LDF film. We haven't run into any issues with the metallization vendors that we've used. It They come back to us and say it basically behaves like polypropylene.
Thanks. And then lastly, I have one last question, and that is, what's the process to begin the consideration for a sample opportunity?
Oh, okay, great question. Typically, the first thing is to contact our team, either myself or Sean Walsh, who is our chief marketing and sales officer. We To get into really detailed discussions, we prefer to have an NDA in place. That way we can probe what your requirements are, what your design specifications for a capacitor are, and that can help us in understanding what we need to deliver to you. And then obviously, if we have that two-way NDA, we can give deeper data than what you've seen in the presentation that I just gave. So we start with a discovery meeting where we um, share as much data as we can on the current state of the material. We get as much information as we can in terms of what specifications the manufacturer needs, and then we just work from there to determine, do we have a film that's in the right thickness and the right geometry for that manufacturer? What is our timeline to getting that film? Does it need to be metallized? Does it need to be slit? That sort of thing. And then I'd like to think that we're very collaborative and easy to work with. Based on the feedback that we're getting from the multiple manufacturers we're currently working with. Pat myself on the back here, but we have typically when we start working with a company, we develop strong relationships quickly. Um, so contact me and we'll figure it out from there.
Thank you, Mason. And I will share your email address here in just a minute. Of course, when you say that's the last of our questions, we have more. So if you're welcome, you want to stay with us, Mason, please do. Nick from CSI has asked, can you talk about DF at higher temperatures?
So for the LDF film, the dissipation factor stays more or less constant out to about 150 degrees C. Once you're up around 160, that's around the melting point of the polypropylene, and then it starts to shoot off. But when we do comparisons with commercial BOPP caps, we start to see that dissipation factor inch up around 125 C. For LDF, it's stable out to about 150 degrees C. For the HDC film, the thermal response is a little bit more complicated. We have a technical white paper, and I can share that with you if you're interested. And that shows frequency response. It shows temperature response, and yeah, HDC is its own beast. It's a little bit different than LDF. It's not a one size fits all type of material. It's definitely a material that's more suited towards lower rep rate pulse power type of applications.
Thank you, Mason, and I appreciate the opportunity to share that technical white paper when we share the recording and this presentation. Santosh has
Cool.
another question for you related to positioning. What is
Sure.
the best base film to sustain max temperature, especially related to EV and HVDC applications?
Yeah, I think LDF film is probably the better solution for that. Um, it's the because it has the low dissipation factor, it's not going to self-heat. HDC has the high dielectric constant, but the dissipation factor is higher than LDF film. So it's if you're looking at EV, we're really targeting the LDF film to compete in that region in that application.
Okay, thank you. Another inquiry from Stephen Bagdy. I saw images of the test master roll. How is it uniformity of a 6 film? Can you do large uniform rolls?
So for the LDF film for right now, we're limited to about 3,000 meters for a roll. When we move into full production in 2027, we'll be able to get, uh, you know, 40,000 or 40,000 or 40,000 meter rolls. Standard rolls that will be in the same sort of format as polypropylene. Our thickness uniformity for our HDC film, which is our current commercial film, it's usually around 1.5% relative to the average thickness. HDC film is 6, 8, and 12 micron. Um, that we have commercial for offerings. We can make targeted thicknesses if we work with a company for a custom solution. For LDF, our thickness uniformity is around plus or minus 3.3% right now. As we move towards the commercial manufacturing on the large scale lines, as we scale up, we anticipate being able to hit the same sort of targets that BOPP hits. So routinely, we measure around, let's say, 0.9% variation for commercial grade BOPP. So it's very, very tight tolerance.
All right, thank you. Another question, and we talked about this, Mason, when we were looking over the presentation and potential questions we would get, is related to cost comparison to BOPP. Can you
Hmm.
share any idea about what that might look like, understanding that there is high value for what we've done?
Yeah, so I mean, obviously this is one of the main things that's going to come up over and over for questions. Um, we're in the process of putting together our COGS models to understand how much it would cost us to make the film, of course, and that changes from where we are right now to when we get to scale. Um, The good thing about this material is that the majority of the material is actually standard polypropylene. So you're not looking at a situation where the cost is going to be, 5x or 10x polypropylene for that added performance. Um, Obviously, there's some added raw materials costs using the high TG material that we layer into the LDF. Um, but it's not going to be in a situation where it's in the same price point as something like Pen HV or PPS. We'll be able to come in at much lower temperatures. And one of the things that we try to stress when we talk to people is that it's not just buying microfarads per dollar. It's buying microfarads per dollar per unit time. So if you hit those long lifetimes that we're targeting, you might pay a little bit more for the film up front, but then you have longer long-term stability of the capacitors that you're making, and there's value obviously added in that as well.
Thank you. All right, one more question.
Okay.
Has your testing been oriented towards DC applications primarily?
So far it's been for LDF has been oriented towards DC applications. That's correct. We are actively working with multiple cap manufacturers, some of whom work in the AC space, and we're going to start those programs shortly. But right now, it's mainly been in DC link type of capacitors. Yes.
Awesome. Dr. Rolick, I want to say thank you, first of all, for joining us today. And
Mhm.
I'm looking forward to sharing your presentation, the recorded webcast, and also the white paper that you mentioned. We'll include that in our follow-up emails. For
Okay.
those of you who are with us, know that we run our What's Next webcast series monthly. If you have a topic that you want to hear about, please let us know. Just email us at whatsnext@peaknano.com. Um, in addition to that, you can follow us on any social media channel outlet for more news and information. Subscribe to our emails, and we'll continue to keep you updated on our progress with LDF and HDC. Wow.
I'd also like to thank the audience for the excellent questions.
We have some other questions. We do absolutely answer all questions, and we will take those up personally in your email. Dr.
Okay.
Woloch and I will take a look at the remaining questions and continue to answer those directly in your inbox. So again, thank you so much for joining us